This is a talk in two parts: morphisms, exact and approximate, and model property preservation, given at the Journées Devs Francophone JDF, the Devs Workshop at Cargis, Corsica, in April 2016. Two parts. We'll start with part one. The outline of part one is we'll consider the need to deal with multi-level model approximation families, provide some background theory on dynamic systems and morphisms, some sufficient conditions that enable exact approximation, and then approximate morphisms to handle departure from these enabling conditions. We'll talk about error propagation and sensitivity analysis. And we'll mention, and not go into great detail, construction of multi-level approximation families. Let's look at the need to consider multi-level model approximation families. Systems may be modeled at different levels of spatial extent and resolution. Example, municipal, county, state. Models may be constructed at coarse abstraction levels that support faster simulation. And, for example, abstract models may be used for model checking. But there's a problem, for example, given by a paper at this conference, that models may, such abstractions may not carry all the information required, and that was shown in an example of a video game, like Pac-Man. Models can be constructed at high fidelity that are purported to be closer to reality. But then how well do we know the details? So how can we assure that errors introduced in the aggregation-disaggregation processes lie within acceptable limits? Interoperation of models at different levels of resolution presupposes effective ways to develop and correlate the underlying abstractions. Thus, the need for multi-level model approximation families. A useful methodology for integrated families of approximation models would allow flexibility in calibration and cross-calibration, application to diverse frames and properties, as we'll discuss later. An example given in this conference where there's a watershed modeled at different levels of abstraction with components such as watershed and two levels of abstraction for that, mountain models and basin models. And each of these can be at different abstraction levels, and then they can be combined to have compatible compositions using the system entity structure. For example, four such pruned and transformed composition are shown here. And then the question is, on what basis should their predictions about water accumulation be considered? Comparing the simulated and observed daily flows for one period. What if they disagree? Which one is correct? Dynamic systems and morphisms provide a mathematical basis for dealing with the kinds of questions that we just looked at. First, the framework for modeling and simulation, which we'll discuss, provides needed concepts for abstract model construction, including models, simulator separation, and experimental frames. Systems theory, which is more meta level, generalizes finite state and linear theory morphism construction. And these concepts support exact model simplification. This framework enables system morphism concepts to be extended to handle approximate model construction and error propagation analysis. First, let's review the stratification of system knowledge or specification levels in the theory of modeling and simulation. As we go up the levels, we introduce more system knowledge or ability to specify the internals of the system under study. So we go from observation frame, where there's just knowledge about inputs and outputs and time bases, and up to observing the input-output behavior, which is the values of inputs and outputs over time. And next level includes the knowledge about the internal state of the model to give input-output functions. And then next level we'll consider is input-output system, which includes knowledge of how the state transitions under inputs and how it produces outputs with these from states. Associated with the levels of specification are morphisms at each level, and the morphism at any level deals with the placing of correspondence into correspondence of the knowledge elements that are available at these levels. So at the I/O frame level, we can only put into correspondence the input and output interfaces, while at the relation level, we can put into correspondence the input-output pairs, and it may be that they're equal, which would be a strong input-output level morphism. At the next level, we would be able to put into correspondence the functions so that the models or systems may have be able to be said to have the same input-output functions, and that would be a strong form of behavioral equivalence. And then at the next level of systems, we may be able to put into correspondence the states and the state transitions under inputs that are also in correspondence. And this would be typically called homomorphism or isomorphism if the mapping between states is one-to-one. The modeling and simulation framework introduced in the theory of modeling and simulation has major elements such as the source system, the model, and the simulator, as well as the experimental frame. Abstraction is defined as a valid model simplification and is relative to one or more experimental frames. So if we talk about a base model and a lump model and a morphism, it could be exact or approximate, and how valid it is relative to the base model or relative to the source system is partly determined by the experimental frame. So experimental frames determine validity of abstraction. simplest case, consider a state mapping from a base model to a lump model. Typically that is many to one, although it could be one-to-one for isomorphism, where corresponding states must have the same output. This means that the mapping must refine the output partition on the states of the base model. That is, any two states that have the same map to the same state in the lump model must have the same output. Then if we look at the partition of the state and iterate the transitions successively, then the states typically diverge so that two states in the same output block will go to different output blocks under a transition, like shown here. However, if we iterate successively, finding the partition each time, eventually we will come to a partition which is called congruent, in which states that are in the same block always go to states that are in some other block. They don't get separated by transition. And at that point, we have both ability to have states that maintain the correspondence with the lump model, but also have the same output, and that would constitute a strong homomorphism from the base model to the lump model. This kind of correspondence would look like this, where here we're allowing multi-step state transitions between times at which we actually put the states in correspondence. But this is just to illustrate the generality. We'll stay with a single step transition in the further discussion. So some conditions that enable exact abstraction. Finite state theory provides algorithms employing congruence relations, state set partitions, and output refinement, such as we've just quickly reviewed. Linear systems developed a model realization theory that was shown to be essentially equivalent to the finite state theory. Probabilistic automata provide somewhat different lumpability criteria, but eventually those can be shown to be equivalent to the other two preceding kinds of theories. These concepts were generalized in dynamic system theory within the modeling and simulation framework. So let's look at state system homomorphism, exact and approximate. Homomorphism concepts are borrowed from finite state automata and require base and lump models to remain in state correspondence over time. So if we have a mapping, as we've seen before, from a base model state to a lump model state, and we make a transition in each, then the correspondence should be maintained, as we've seen just a while ago. However, if there is only approximation, it may happen then that the correspondence is not maintained, and that the transition for the lump model, rather than being an exact agreement, actually has an error. And so the lump model goes to a state that is no longer in correspondence with the base model. But we can consider this to be a departure from the exact mapping. So we can call that the error introduced in the transition. And now if we consider another subsequent transition, then the state which we actually got to in lump model makes a transition and introduces more error, the error after two transitions between where the state should be and where it actually is in the lump model. And this error can be considered to be the accumulated error introduced by state transition step by step over time. The question is whether this error will accumulate and grow without bound, or whether it will die out and reach either a steady non-zero value or maintain a close to zero value. A parameter morphism is a homomorphism that maps the parameter space of the base model into that of the lump model while defining or while supporting the state mapping for the homomorphism. So typically models have parameters, and really those define a class of models rather than a single one. And parameter mapping maps elements in the base model space to elements in the lump model space. Parameter morphisms retain valid simplification under changes in parameter values, so that if there is a morphism from a model with set parameters and we vary the parameters, as long as we then map the parameter values to new ones in the lump model using the parameter mapping, we should expect the same preservation of the morphism from base to lump model. This supports cross-calibration in multi-level, multi-resolution families, allowing us to relate one model to another, or one class of models, or parameterized model to another. We look at how the conditions discussed so far apply to coupled models, where we block off components similar to blocking of states, but at the component level. So we have a base block mapped to a lump block, and so on. And the couplings between the blocks also have to be preserved in couplings at the lump level. So each component has a component aggregation of its states into the from the base into the lumped corresponding lump block. And rather than go into great detail, we'll state that the aggregation theorem not only must there be homogeneity within blocks, but also the interblock element-to-element interactions must satisfy coupling indifference conditions. What these are particularly is stated in the theorem, sufficient conditions for aggregation, that there be a partition on the components of base model for which, one, blocks have homogeneous components, and two, the coupling indifference conditions hold for all pairs of blocks, and three, the base model output is computable from the block model census counts, that is the count of states and not going finer than the state level. And the indifference means that a component within a block cannot tell from which particular component in another block it is receiving inputs. So C is indifferent to A or B in this case, and likewise A cannot tell whether it's sending input to C or to D. It sends basically to anyone in the block. So that's indifference as to identity within the block. We can apply this same concept to an example of lumpability applied to linear discrete time systems, where the components, individual components, are at the coordinates in the vector, state vector, and the components are lumped so that x1 and x2 are mapped into y1, and x3, x4 are mapped into y2 according to this averaging kind of mapping. And likewise, the parameters of the elements that of the matrix relevant to the each of the blocks are aggregated as well with this kind of averaging, so that all of the components for mapping x1, x2 into y1 into x3, x4 are mapped in this way. B1, B21 is obtained by this sum of, or averaging of these four components here. And then the lumpability criteria requires that the individual components A31 equals A41 and A32 equals A42 along these rows must be equal in order to produce an exact homomorphism. So here the base model transition function is expressed as a matrix of coefficients. The lump model transition function is of lower order with coefficients derived from aggregation of base coefficients. The state mapping aggregates base states to lump states. The lumpability criteria provides sufficient conditions for preservation of the state mapping over time, the homomorphism as we discussed earlier. So this is an example of a parameter morphism that provides a homomorphism at the state level. Now, we can't rely, especially as I'll show later, on morphisms being exact in the real world. So we'll discuss approximate morphisms that are able to handle departures from enabling conditions. Approximate system morphisms loosen up the strict requirements of exact system morphisms. The propagation of error that results is characterized and related to the dynamics of the resulting lump model. The error propagation can grow or attenuate with time depending on the lump model stability characteristics. So we can analyze a base model and a block partition construction for error departure from exact morphism conditions. And we can simulate and compare base and lump model behavior for sensitivity to error propagation. In our example of the linear system, the approximate lumpability would allow coefficients of the matrix to deviate from the sums as required. So in this case, for example, G minus E is not equal to G, it differs by E, and in this case, 0 differs from E, so the lumpability conditions are not met for this upper segment of the matrix. So when we map into the exact matrix 0G, which is the average sum, then the mapping is not necessarily exact. And so the error can be measured by x1 plus x2 minus y1 all squared, and x3 minus x4 minus y2 all squared, and taking square root. And the theory predicts that the gain G, which turns out to be a feedback from 1 to 2 and 2 back to 1 in the lump model, determines the error propagation characteristics. The error decreases over time when G is less than 1, when this gain is less than 1. Otherwise, it increases. And the closer to lumpability, the faster the error disappears. So the closer E with G less than 1, it decreases over time. So if we examine this table of simulation results, starting down below here, we see that for G equal 1.2, bigger than 1, and an error of 0.1 from the mapping, that the error increases explosively over time. And as G gets smaller, the error increases, but less in a lesser manner. And as the value of G gets less than 1 at 0.8, the error is 0, then the error is 0 over time. For values of G less than 1, 0.8 for example, and E not 0, we have now that the error decreases over time. So that, for example, when the error is fairly small, 0.001, after 5 time steps, it's become very, very small. So the critical factor is this gain level in general. You can define that for linear systems, and that the gain has to be less than 1 for the error to disappear over time. So the application to evolving or making over time model approximation families. The approximate model construction methodology supports integrated families of approximate models. Approximate models are indexed by the experimental frames in which their conditions approximately hold, and error propagation conditions in these frames can be estimated. As field data is ingested for verification and validation, or calibration, any one of these models propagates information to others from which it is derived, and which are further approximations of it, thus maintaining a coherent model family. So integrated families of approximation models support 1, estimating trade-offs in accuracy and execution time, and 2, choice of approximation meeting analysis needs and time constraints.